this. Invite me to this nice school. So, as was advertised, I will talk about quantum ergodicity. That's an old and a new subject together, and it's very big. So I'll be very selective, and maybe because of my own preference, like condensed matter background, I will be concentrating on many-body quantum ergodicity. There is a lot of work which was done with heavy nuclei and maybe billiards and things like that. I will just mention those on passing, but I'm not going to talk much about them. So this field is interesting. I think it got like sort of a new birth well, after cold atoms, but in particular there was a very influential paper by Marcus Riegel in 2008, and actually it brought on light other papers, and two of them by Max Rednicki. They were sort of written in the 90s and sort of forgotten, and I will talk about those as well. So, because there is a lot of numerics, I decided to rely on slides. I will maybe occasionally use a blackboard, and I know there is always a tendency when you use slides to go faster. So if you stop me with questions, it will be helpful, I guess, to everyone to slow down. So I basically thought that maybe I'll split the lectures in kind of two parts. So one, I will talk about quantum ergodicity and the eigenstate thermalization hypothesis. Basically, I will throw out the concepts and when they work, when they don't work, and maybe show some examples. And then in the second part, I will try to show how you can use this eigenstate thermalization hypothesis for some statements in equilibrium, non-equilibrium thermodynamics. Again, some of them we know very well. These are laws of thermodynamics. Some we already know very well. These are fluctuation theorems. But I will also mention them, but mostly in the context of expansion. In a sense that, as was mentioned many times, we have p to the minus beta w average equal to 1 or whatever ratio of partition functions, but these relations are not very useful in big systems unless w is small, because taking something which is very big, extensive, and exponentiating is just useless. So, and there will be many fluctuation relations, so I will talk about connections with fluctuation dissipation relations and so on. So I also want to apologize, I'm still a little bit jet lagged, so I will frequently say wrong words, so anyway, I'll try to be as coherent as I can. So let me start from some very, very general statements. So again, loosely speaking, I want to say there are sort of three approaches and various interpolations between them, how we can describe dynamical systems. And even though it's quantum ergodicity, in this talk I will be frequently mixing classical and quantum. I will try to emphasize when quantum mechanics is important. So first is purely microscopic. So we just write some microscopic equations of motion, say Hamiltonian equations of motion. And in principle, if we know our Hamiltonian, we know everything about the system. So, but as we know, there are lots of things hidden beyond words in principle. So, and in particular, these approaches, they work only for really small few-particle systems. So even if you have like from this cartoon, you can see that if our dynamics is chaotic, then very, very small error, which we'll introduce in the beginning, it can be either numerical error, or error because our Hamiltonian is not purely isolated, or error because we don't know all the coupling constants in the Hamiltonian, or maybe initial conditions are not perfectly known. So any small error will propagate, and soon it will be very, very expensive in classical systems to follow the trajectory. There are exceptions, and these exceptions are integrable models. It's those which we like to play with a lot. Well, there is another approach. It's just to start from statistical physics. So we just say that we have some partition function which basically gives us a microscopic probability distribution. And after that, we are saying let's use Hamiltonian dynamics, but perturbative. So, and using this perturbation theory around the partition function, we can again make many predictions, and in particular all the scuba-type responses, conductivity, any susceptibility, fluctuation dissipation relations. So lots and lots of statements were derived in this framework. Well, now people are more interested in more sophisticated approaches where dynamics is partly Hamiltonian because, again, there is a bath, so there's some work on inlet dynamics, but it's basically still a Hamiltonian dynamics where you try to focus only on subsystem and somehow throw out approximately the rest of the system. And there is, I should say, third type of approaches. It's mixed. It's not fully microscopic, not Hamiltonian. It's not purely statistical in the sense that it doesn't rely on proximity to equilibrium. And we also know these approaches very well. So there are kinetic equations, master equations, Fokker-Planck equations, well, as we heard, Ginzburg-Landau equations, and so on and so forth. But basically, this amounts to writing some equation for probability distribution, which should satisfy detailed balance, which usually is put by hand. So we know that if the system is in equilibrium, then d rho dt should be 0. And it's obvious it should satisfy conservation law. Well, if there are additional constraints like total energy is conserved or whatever, you can also put them back. So in a way, I will of course not connect all of them together, but I will show some hints how using newer insights, in particular from this quantum ergodicity eigenstate stabilization hypothesis, we can sort of see how these approaches are connected. So there is no magic, there is no disconnect between them. Good. So let me just show again one more basic slide. I already told you that there is a chaos which makes a problem, but again, a problem in simulating things microscopically. But again, usually, at least when I studied at school, we were saying this words in principle. In principle, if we can solve, 10 power 50 equations, we could get full information. But let me just try to argue that maybe this in principle is actually fundamentally flawed. So let me imagine that we don't have the universe to begin with. We just start building it, particle by particle. So if you have 3 particles, we can ask, so can this universe describe itself? And obviously no, because we even cannot store the information. So, Well, how we can store the information. So we want part of the universe to explain another part, basically. And well, if you want to describe how the 3 particles collide, there is nothing left to describe. So let's start adding particles by particles. So if we have 100 particles, we maybe describe the 3, because we will use other 3 to simulate experiment, simulate the 3, and other whatever remaining 94 to store the data. But if we want to simulate with this 100 particles, whole universe of 100 particles, it becomes much, much harder than even with 3. Because we need tremendously more information. Like in quantum language, we need exponentially more information. So now we might think, okay, when we reach 10 power 50 particles and someone gave us a tool like a pen to write equations, did it fundamentally change the situation? I don't think so. If 10 particles, you just need to realize that complexity grows much, much faster than any ability to solve problems, to write equations or anything like that, to store the information. So basically, I would say that microscopic approaches, they are very, very useful tools, but they're definitely incomplete. Okay, so how we traditionally connect all these 3 approaches? Well, in classical mechanics, and I assume there were lectures about this, it's through ergodic hypothesis, and it's not really always hypothesis, sometimes it's even mathematically proven. And basically, what it tells us, is ergodicity, well, it tells us that if you wait long periods of time, and now I'm assuming that my Hamiltonian system is Hamiltonian here, and Hamiltonian doesn't change in time. So after long periods of time, the time which is spent by ensemble of particles in some region of phase space at the same energy, and in principle, if there are other conserved integrals quantities like momentum, angular momentum, or maybe something else, number of particles, we should also fix them. It's just proportional to the volume of this region. So in simple words, we can say classical ergodicity is complete delocalization in the phase space, satisfying the constraints. And coming back to this example, like ergodic statement will tell me that if I have chaotic cavity, then if I look into long time average of a position of the particle, then what I will get is just basically microcanonical ensemble. So which is a more fancy way to say that my particle will be will have random direction of momentum and one random coordinates. So magnitude of the momentum will be fixed by total energy. Well, if we have integrable systems, then clearly we have more degrees of freedom, and I will be talking about this in detail later. But from this picture, it's clear that system will still randomize itself, but with a constrained phase space. So it's not that integrable systems are not ergodic; they just have more constraints. And in this example, in order to have ergodicity, we had to introduce typically some irregularity of the cavity. But it turns out that most interacting many particle systems, they are chaotic even with regular interactions. And this will be my main subject of my talk. But before going to ergodicity, let me just show a very famous example, and probably most of you know about it, when ergodicity doesn't work. And this is like Fermi-Pasta-Ulam problem. I guess it's last paper by Fermi, and he actually didn't write it himself, but he initiated it in 1954. So they had computer to simulate nuclear reactions, but Fermi was a curious person, and they decided to study ergodicity of thermalization in a one-dimensional chain. So, and of course everyone knew that if we have harmonic chain, that the system will never thermalize. Because if you want all occupations of normal modes are strictly conserved, or classically all energies of normal modes are strictly conserved. So what they did, they added nonlinearity and they played with nonlinearity. So they added 3 types of nonlinearity. This is a particular one. And they even called type 2, type 3 or something like that, Fermi-Pasta-Ulam model. So it's basically quartic nonlinearity in interaction, which leads in cubic nonlinearity in equations of motion. And then, to avoid fast oscillations, they looked into slow variables. So these are basically our integrals of motion of a non-interacting system. And what they expected to see is that if they, by modern language, they do interaction quench. Actually, I think when Alessandro attributed first quench papers to 2002, Fermi-Pasta-Ulam problem is actually interaction quench. You start from non-interacting chain and suddenly turn on interaction. Maybe, yes. Yeah, but it's perfect, well, classical quench problem. So they hope to see ergodicity. So if they would observe how these energies behave in time, they start in a particular state where only one mode is occupied, so it means that all energy is stored in one mode, and energies of all other modes is 0. And then as time evolves, you just see that first things look okay, because energy definitely goes down from the first mode and goes up into other modes. I believe there are 32 sides here, so in principle you should see all the numbers up to 32. But somehow it goes up to 5, maybe just tiny bit to 7, and then it's stuck. But instead of equipartition, when sort of all energies will go to the same line, they go to some crazy regime that basically everything comes back. And you might say, if I wait longer, this is a little bit smaller, then it will go down, 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 but actually even this is not true. There are super revivals. So eventually this revival will go down, 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 but then it will go up, up, up. So if I go to like, I don't know, 5 or 6 revivals, I will get almost 100% energy back. So in principle, even in equilibrium, it's not surprising to have fluctuations, but not such fluctuations. you expect fluctuations maybe like few percent. So we see that this system, despite it's nonlinear, and as far as it's known, it's non-integrable, it's still non-ergodic.
Just a question. So in the previous plot, you were plotting those energy variables that you wrote down on the different sides.
This is in momentum space. Yeah, please ask me questions, by the way. Yeah, so when you write on slides, you forget to say. So this is a momentum space. So these are eigenmodes of non-interacting system. So you occupy first momentum mode. It just imagine that you're doing something like that. So if you have a circular shape and then you just squeeze it. So you do something like that. And then this thing starts to oscillate like this. And then eventually you expect that this energy will be dissipated into other modes and this will thermal.
So in normal systems with a finite entropy, you have these recurrences, right? That any state you started out with, you repeat.
Right.
So you're not in that regime, right?
No, these are exponentially, yes. So those recurrences are exponential. Even in statistical physics, in equilibrium statistical physics, there is a room for very rare fluctuations. And for example, in the previous talk, they were responsible for switching magnetization. So it's not that they're not there, but they're exponentially rare. So here, it's not shown in this plot, but what you can show, the dynamics is self-similar, in the sense that if I keep gradient of the phase constant, initial phase, so this Q means first mode occupied, means my momentum is whatever, 2 pi over 32. So if I keep this gradient constant, I go to 64 sides, but now I occupy second mode. I go to 128 sides, I occupy fourth mode. Then dynamics is completely self-similar. So this separation changes with system size, but not exponential. Yes, it turns out that later Fermi was, I guess he thought they were unlucky, but actually they were lucky because they started really new field. And there is a journal paper in Scientific American by David Campbell and collaborators, which title is Fermi-Pascal-Lamb problem and birth of experimental mathematics, or something like that. So maybe it's a little bit overselling, but definitely it was beginning of new field. But it's known that if you start at slightly high energy, different initial conditions, or whatever, the system is fully ergodic. It's still not known whether there is a transition or crossover between the two regimes, at least as far as I know. Okay. So it turns out that for few body systems, actually around the same time, people thought about this, and in particular probably heard about Kolmogorov-Arnold-Moser theorem, which I'll mention in a second. So it's a situation when we have few degrees of freedom. So it's n, but n is not a big number, it's maybe 3. So originally, Arnold, well, I guess it was mostly PhD work of Arnold, as far as I understand the theorem. They were interested in stability of like planet systems, so they were interested in few body systems with chaotic behavior, with slightly, just they were interested in the onset of chaos in the system. It turns out that this theorem found lots of applications, and probably many of you know Kapitsa pendulum. So if you take a pendulum and start shaking it, it can go upside down and be stable. It's also part of this category, so where you can understand why things are stable from the point of view of this KM. So, but basically, for few body systems, the situation is more or less understood, at least mathematically. So if you have a system with n degrees of freedom and n integrals of motion, these are commutators, but think about them as Poisson brackets, then it's just known that trajectories which are confined to constant integrals of motion are some tori in multidimensional space. And then, what was proven mathematically by Kolmogorov, Arnold, and Moser, that if you don't have degeneracies between frequencies, So it's basically, think about this, you have radial motion and angular motion. If they are not perfectly degenerate, then it will take you some finite amount of interaction to break down integrability. So otherwise, you'll just slightly modify this tori, but the system will sort of still move in the vicinity. System will become chaotic within a tori, but it will won't go to another tori. So classically, it was understood that thermalization or ergodicity or chaos it occurs through destruction of KM tori, and you need finite amount of interactions to cause ergodicity.
Is there an easy estimate of the amount of interaction string that you found?
Yeah, it's just first order perturbation theory. So basically, what you do Fermi golden rule. It's for classical system with the same thing, and then you just check that basically transition matrix element between two resonances is comparable with the lifetime which you get within the same Fermi golden rule. So it's a very simple criterion.
So does this theorem explain your previous slide that if beta
well, that's exactly so there are lots of actual issues with this theorem once you go to thermodynamic limit or once you go to quantum system. Because we know if you say about gas in this room, you barely need nothing to thermalize. Maybe there is something and very small, but this something should be so small that it's basically zero. So it's something which goes down with the system size. So, and as usually in many body physics, you can make statements precise only when interaction is small compared to some scale which goes down with the system size. So like for example, you can make high temperature expansion precise if temperature times energy span of your Hamiltonian is less than 1. But in thermodynamic limit, energy span is infinite. So this sort of statements become useless. So you really need to know how to do some sort of a series. And as far as I know, it hasn't been done for KM theory. But there is a strong numerical evidence that it does work for this Fermi-Pasta-Ulam problem. Because you can still write this criterion. It's like doing first order perturbation theory. So like doing Fermi-Golden rule. And from this Fermi-Golden rule, estimating when you get a chaos. And these were papers by Chirikov, Israilov, and well, mostly them. And from those you can get a criterion, which is an estimate up to a prefactor. And then there was a numerical study of spectral entropy. So it's basically, if you want, it's like a von Neumann entropy, where you look into, or Shannon entropy if you want, where you look into occupation of your modes after a long time in the Fermi-Pasta-Ulam problem. And then you realize that if the system thermalizes, then this occupation, these are probably energies, not occupations, but energies, because you know in equipartition they will be the same. If the system thermalizes, then these energies will be the same, and this entropy will reach maximum value. If on the other hand, everything stays in one mode, then this entropy will be 0. So what you can do, what these guys did in '85, they looked into long time limit of this entropy as a function of interaction. And they see that there is a critical length. So this, by the way, is intensive interaction because it's total energy divided by system size. But if you fix energy density, it becomes well defined in thermodynamic limit. So there is a curve beyond which it seems that the system thermalizes. So it's basically, if you want this regime, the system is non-ergodic. Here's what it is ergodic. So this is an example where it seems that there is an onset of ergodicity in thermodynamic limit. When I spoke to Israilov about this, so he is basically the author of this, with Chirikov, they wrote this criterion based on first order perturbation theory. He mentioned that it looks like in second order perturbation theory, you should destroy any counter, right? And the reason is that in first order perturbation theory, you can imagine that it's sort of hard to match if you have sufficiently big separation between frequencies, it's hard to match these frequencies within small interaction. If you think about quantum mechanically, within Ford-Golden rule, you cannot give enough energy because there is finite energy mismatch. You need finite interaction to do it. But if you have many multi-mode resonances, you can always exchange energy. So basically, one mode goes down, another goes up, and there in the system you can always find nearly perfect resonances. So from this point of view, according to him, it seems that at very long times, even infinitesimal interaction and thermodynamic limit should destroy everything. But it doesn't happen to measure. So this is entropy. So it's basically, think about this as indicator of mode occupation. When it's 0, it means that all modes are occupied, so you're in thermal equilibrium. If it's 1, it means that only one mode is occupied. Oh, it's here. It's normalized entropy. So you just define Shannon entropy, spectral entropy, if you want. Kolmogorov. And then look into ratio of maximum entropy minus your entropy and maximum entropy minus whatever.
This is entropy
as a function of interaction. So interaction increases here. Well, it's here, it's log interaction. These are weird excesses, but then curve looks nice. So interaction increases here. So here you have very, very small nonlinearity, and then it's localized. And then you increase, and then it becomes chaotic. So they make the statement that it looks to be right in thermodynamic limit, because you see they look into different system sizes and everything more or less falls on the same curve.
Beta is the inverse temperature?
No, eta is entropy, sorry.
Oh no, beta.
Oh, beta, yes. No, beta, sorry. Beta is nonlinearity. Yes, that's a bad notation. Sorry. It will be inverse temperature everywhere in the rest of the talk. So, but it's standard notation for FPU. So they introduced nonlinearity, they called it beta. E is the total energy you put into the system, and N is the system size. So you keep energy density fixed. So that's why it's well-defined thermodynamic limit. Okay, good.
So, in summary, the summary of the plot is to make beta large enough, it will thermalize.
Yes. Yeah, right.
How do you decide when you evaluate this entropy?
So can you say?
So this entropy is evaluated for the moment of time.
Yeah, they looked into very long time. You're absolutely right. So when we deal with classical systems, there is always a question, did we wait long enough? So I don't know exactly what they did. So they looked long enough time, but whether they looked into times getting longer and longer, in principle you need to check that if you wait longer, this doesn't change. But they average over very, very long times. So these are extremely long times. So it's still, but that's why it's not a proof. It still might happen that at exponentially long time the system will thermalize. So it's not a proof. Okay. So, but my talk is about quantum ergodicity. So let me just set up the language. And this is the language for now. I will talk about Hamiltonian dynamics. In the last part of my lectures, I will try to talk about Hamiltonian dynamics, but in bigger systems. So when you have two systems and mass. So, but for now, at least for this talk, for sure, I confine myself to the situations when we start from an isolated quantum systems with time-independent Hamiltonian and some arbitrary initial state. So let me introduce first in the setup the density matrix. I'm sure like every single one here knows what it is and uses it and so on. But yet there are lots and lots of confusions. At least sometimes I hear people are saying if you know, I don't know, your density matrix of your universe, you can measure everything, which is, of course, completely wrong. If you have your density matrix of universe and you have exponentially many copies of the universe, then you can measure it. It makes really big difference. But sometimes the difference is not important when we look into many observables, but sometimes it's very important. So, right. So let me assume that we start each experiment from a pure state for now. And this state evolves with some Hamiltonian h. So I can always write this state in the eigenbasis of my Hamiltonian, and then evolution is trivial. Then I will be interested in expectation value of some observable, which is, as we know, a Hermitian operator. And then basically what I do, I write expectation value, plug it in this expression, and find something very simple. So this is, as we know, sum over double sum n m, coefficients Cn star Cm, and oscillating exponents, and the matrix. Good. Now, let me say maybe trivial words, but they're very, very confusing, including myself. In order to measure this expectation value, you have to perform many measurements. Single measurement doesn't give you expectation value. So, but each measurement corresponds to a new experiment. So, if we were able to start experiments with exactly same psi naught, then I can say, okay, this is what I measured. But in reality, you'd never start from the same psi naught. You start from a different psi. Because the way you prepare the system is random. After all, even when we cool cold atom gases, we think about them. Like if we do it, well, when Ketterle does it in Boston, he connects to Niagara Falls, right, through electricity grid. So all these fluctuations which are there, they translate to cold atom. So there is no way you can cool the system to pure eigenstate. Maybe if it's a small system, you can cool it down to a ground state, because it's separated by a gap especially. At a finite temperature, no way. So therefore, when we do measurement, when we want to find expectation value, we always do both average over quantum fluctuations, if you want, and statistical fluctuations. So this bar here, and bar will fluctuate from slide to slide, but here bar means statistical average over initial noise. And let's call this statistical average as rho and m. This is our density matrix. And then we just see that this density matrix evolves in time, as we all know. So one thing I want to emphasize, that there is a big assumption here that Hamiltonian is not fluctuating. Because you might say, but what if in each experiment I will get different Hamiltonian? Well, that's the simplest way to get decoherence. Usually we say there is some mysterious bias or whatever. But we can say, no, we always have pure evolution. But each time we have slightly different Hamiltonian. One, say, with subway nearby, one without subway nearby. So this immediately introduces uncertainty in my evolution. And this can be tracked with this Limbladian formalisms and so on, dissipation. Yes?
For the preparation of state, in many experiments, they do send the state through a measurement, and then
Right.
I mean, that's on for the state, and that in all those experiments, the state.
Yeah, for few particles there is no problem, absolutely. Yeah, you can always prepare spins up with very high fidelity. There's no question. But once you go to 10 particles, I can ask you, can you prepare, I don't know, system of interacting 10 spins in an eigenstate? Man, it's difficult. Actually, with ion traps, they can almost do now 10. But even this is hard. If I ask you about more complicated systems, no way.
Anatoli, and you cannot argue some kind of criticality?
Oh, that's coming, yeah. I just want to set the stage. Okay, so density matrix is basically, I want to repeat myself, it includes both statistical and quantum fluctuations. So it has everything. Okay, so now let's go to ergodicity. So as I said, in classical systems, the statement is very simple. Maybe proof is not, but the statement is simple. You just say in long time limit, your time average of your phase space variables, so x sets for my all possible phase space variables, spin directions, coordinates, momenta, whatever you want, it will be given by microcanonical average, and therefore any observable will be so. What about quantum systems? Or I should say maybe quantum language. Because again, very often when people refer to quantum ergodicity, they just refer to language of quantum mechanics. You have to be careful which statements are really sensitive to the fact that you're quantum and which is just consequence of the fact that you are using language of quantum mechanics. So in quantum mechanical language, I know that my evolution is trivial. There are no nonlinearities, it's just usual linear dephasing. So, and because evolution is so trivial, I cannot relax my density matrix, right? So if I look into this time average of the density matrix, I will get, well, something which describes me just initial probabilities to occupy eigenstates of the Hamiltonian, but there is no reason for this to become microcanonical density. So it means that thermalization must be hidden in the structure of eigenstates, because the devil of complexity is somewhere, right? So it's not that it disappeared, but it's just hidden somewhere in the structure of the state. So maybe this coefficient L. And this was realized very, very long time ago, but for Neumann and then a lot of people explored this fact. So, but basically what von Neumann originally said that maybe we should look into observables. Density matrix is too complicated, clearly doesn't thermalize. But does not mean that if you look into a particular correlation function, it will not thermalize. So in particular, what we want to understand whether expectation value of some quantity, this can be magnetization, correlation function, or whatever, in the long time limit will be the same as expectation value in some thermal state. And long time limit is usually understood at long times, at almost all times. Because of course if my average, time average is not representative, if I have splashing back and forth, we won't call it thermalization.
So this is a statement for a closed system, right?
Yes.
If I'm just looking at a subsystem and then the reduced density matrix kind of course.
Yes. Yes. That's
Is this only a statement about unitary evolution?
This is yes, but thermalization is definitely not. But it's actually the same question, because I can always look into subsystem as sort of unitary evolved bigger system. Or I can say it's a non-Hamiltonian dynamics for a subsystem. But for now, I will stick to one system, and later I will go to many, two, not many.
So, I guess if something thermalizes, we can extract some kind of a temperature.
Yes.
And is it guaranteed that whatever variables will thermalize, they will give rise to the same temperature?
Nothing is guaranteed, but I will show what typically numerics, what numerics show, right? There are no proofs beyond this point. I should probably put it in the slide there.
The fluctuations of preparation which were averaging over it.
Yes.
Are there any constraints on what kind of fluctuation you...
This is your initial density matrix. Yeah.
You're just characterizing
Right. So everything is here. So this is actually not C alpha squared. These are averages of C alpha squared over experiments. So whatever is your... So you can say, yes, so you can say, maybe I always start from a state where these C alphas are already thermal. So that's definitely a possibility. But then you will be forced to say that one eigenstate is not enough. Anyway, I'll go through these things in detail. So, but in a way, just you see, quantum language thermalization is interesting. So in classical language, we have particles which collide, and because of chaos, they lose memory. In quantum language, everything is built in eigenstates, or if you want, these coefficients. But these coefficients, which are probabilities to occupy eigenstates, they don't change in time. So it actually means that my thermalization is like opening a blanket. In a way, I already know. So once I did a quench, same second, my wave function still didn't change. But I already know what my infinite time limit is. It's just hard to measure it. Yes?
Are you speaking from the outsiders, the psi alpha energy
Yes.
in general, that's not...
So I'm projecting to energy eigenstate. I can expand on any basis.
Right, but they won't necessarily be their eigenvalues.
No. I'm just saying in long time limit, sorry. Oh, maybe I skipped the most crucial step. So if I average this over time, yeah, I missed the main thing. Sorry. Yes, so if I average this over time, then only diagonal elements will survive, right? So that's the point. So, but basically, diagonal will survive, but will not change, right? So diagonal elements at time equal to 0 are the same as at time equal to infinity. So in some sense, if you work on the right basis, you don't need to wait until the system thermalizes to find out its properties. Just, you don't know this basis. Okay.
So I'm confused. If you start out with some initial density matrix in a closed system,
Yes.
the density matrix just remains the same, right? Even the off-diagonal elements.
No, magnitudes remain the same, but phases fluctuate. So diagonal elements in the energy basis are the only ones which don't fluctuate. Everything else oscillates. Like simplest example, maybe 2x2 system. So imagine you prepare in X basis. So your density matrix is 1/2, 1/2, 1/2, 1/2, right? So I write this state in the basis of up and down. But then I apply Hamiltonian, which is minus h sigma z. So what happens? Well, I get e to the IHT here, e to the minus IHT here. After a long time, it becomes diagonal. Actually, by the way, any measurement you can think about this way. It's something I didn't emphasize, and I mean, people always say this: measurements of projections to eigenstates. This is sort of things which you need to memorize and take as a postulate in quantum mechanics. But actually, if you think about the measurement, what do you do to measure spin 1/2? You exactly apply strong field along the direction to separate them, because if there is strong energy separation between them, you can move one to the left, one to the right, or do other things with them. But that's really dephasing in this basis. So any measurement is actually you can think about this as appropriate projection to diagonal extent. There's no magic in measurements. And that's, by the way, the question whether do you really look into the object and this is important, or you don't look, it's completely irrelevant. If you dephase, in a sense, if you cannot, so you apply field for a long time, and this time slightly fluctuates from experiment to experiment, or you just don't know it. Suppose I send you spins at random times. Then from your point of view, it's completely measured system. Doesn't matter whether you look at it or not. Can you say louder? Sorry, I can't. Yeah. Yes. Yeah, I'm very slow. I'm coming there. Okay, so next I want to mention is Berry conjecture. He was apparently also one of the first who thought how you can connect quantum ergodicity, classical ergodicity, and this statement about quantum mechanics. And he just postulated, I guess, I actually don't know from which considerations, he just postulated that if you take this particular strange object, psi of x minus small s over 2 and x plus s over 2, and average over energy shell, which contains many states, but still this width of the shell vanishes in limit h bar goes to 0. There's no problem in doing that, because number of levels is exponential, while even in h bar, so 1 over h bar, so there's no problem in taking this limit. And he just postulated that this thing is just Fourier transform of microcanonical distribution. So why he postulated this? Well, I don't know exactly, but I can give you my view on this. So, because this Fourier transform of this object, this strange object, is nothing but the Wigner function. Probably some of you heard about this. It's an object which gives you one-to-one map between quantum operators, including density matrix, and classical objects. So this classical object for density matrix is called Wigner function, and plays the role of quasi-probability distribution, in a sense not positive. And basically, what Berry said, that Wigner function of a small shell is a microcanonical distribution. So that's a less fancy way of saying the same complicated thing.
So what is the normalization factor sigma?
Well, this is basically your phase space volume if you want number of states within this energy shell. Well, it depends how you normalize. So, integral over this over your phase space should be 1. So basically, if you write this integral with 1 instead of Wigner function, well, integrate over x and t, you should get 1. So anyway, it's phase space volume of energy shell. Yeah, that's basically Berry conjecture is. The Berry conjecture said that if we take our system and take a shell which is small but still contains many levels, so in the sense that within any classical resolution it looks like 0 width, right? It's smaller than h bar, but yet it contains exponentially many levels. So if you do this, what we'll recover that Wigner function is exactly classical microcanonical distribution. That's what his conjecture is. And then you probably won't be surprised that if I use this Berry conjecture for some weakly interacting particles, like in this room, and I calculate momentum distribution, I will recover Maxwell distribution. And in principle, I could go to a blackboard and give you derivation, but I won't, because you all probably know this very well. Since average of any power of momentum is just given by average over the Wigner function. That's basically the definition of the Wigner function. And my Wigner function is a microcanonical distribution. It means you can open any books in statistical physics and see how it works. Okay.
Is this conjecture for like any Hamiltonian or just the Hamiltonian?
Well, I like his style a lot. He doesn't pretend to be general. So he always works with few variables, like Berry curvature, its particles in space, or Berry conjecture particles, but makes somehow very general statements. So I guess you should ask him whether he implies it's just for this system or for everything. To me, it's any set of canonical variables. Doesn't matter, as far as I can tell. But you should ask him. Okay, but this was semi-classical limit. What about quantum systems? So now I come back to what I briefly mentioned before. So we prepare the system in some state, then look into long time limit. As I said, we basically average over time. We see that what we get is average with respect to diagonal part of the density matrix.
Question?
Yeah.
Just to follow up on the last one. We would want quantum chaotic system
Yes.
for this.
Right.
So it's not just
Right. That's why I will have to refer to numeric. But it's coming. Yes, of course. If it would be for any Hamiltonian, I would just take right spin 1/2 and prove it in one line, and then say, okay, and then it works. It's subtle. Okay, so in typical situations, actually both equilibrium and not, energy is extensive, while energy fluctuations are sub-extensive. So this you can just prove based on locality of the Hamiltonian if you want. Because if you start from a system with some extensive energy, and then do some interaction range, unless these are infinite range interactions, you will always have fluctuations with scale as square root of the system size. So it's, if you want, central limit theorem, because different parts of the system initially don't know much about each other, and after you do a quench, energy is conserved. There is a very simple proof. So it actually means that if you want to reconstruct thermal equilibrium for any initial state, we only need to say that these matrix elements within some sub-extensive shell are very close to each other. So if this is the case, then apparently there is no contradiction between time average and equilibrium, because we just take this O and N, whatever matrix element, out of the sum, all of them are the same, and then sum of rows sums to 1. So we see that long time limit of the observable really doesn't care about initial conditions.
Is that criterion? So each observable can be.
Well, we should say any local observable. It's actually sometimes people talk about, again, projections to eigenstates, but for this I would like to refer to Landau-Lifshitz. And Landau-Lifshitz says that observable is only object which has well-defined quantum classical correspondence. And in the end, that's what we observe. So any local operator is fine, but if you have, again, I don't know, system of 20 spins and 20 sides, ergodic means interacting, I invite you to write projection as an observable. So projection is not really, I'll talk about this later. But of course, our proof will be challenging because we know there are observables which do not thermalize. So how to exclude them mathematically, it's a challenge. That's sort of the reason why these are mostly numerical statements, not analytic statements. So, and this paper which I mentioned in the beginning by Marcos Riegel and collaborators, which brought a lot of excitement to this field, where they studied some particular non-integrable model, basically it's shown here, where they can find all particles somewhere, I guess here, and then suddenly turn on tunneling, and then they look into momentum distribution. And basically what they see that after some time, their blue curve, which is true dynamics, saturates near microcanonical ensemble. So there is no difference in their calculation between diagonal ensemble and microcanonical when you just pick one state, eigenstate. And then you see the system relaxes and stays very, very close to this state. If you look into canonical, there is a difference, but it's because finite size effect. You know, in canonical, in systems with finite number of particles, you have to be careful. So this is another plot where they look into long time limit of momentum distribution. And again, same story. This is initial, which is very non-thermal. And then if you look into microcanonical and long time limit, they're basically indistinguishable. So canonical is slightly different. So this was basically a numerical proof of this eigenstate simulation. But actually, as Mark Svidnicki like to point out, eigenstate simulation hypothesis is more than that. It's not about diagonal observables only. We might be interested in fluctuations. And if you like fluctuation of an observable in an eigenstate, then it's a very simple exercise to see that this will be sum over all possible eigenstates not equal to n, basically square of OMN. So it's sum of positive numbers. But the sum contains exponentially many terms. So the only way out is that all these off-diagonal elements are very, very small. So diagonal is of the order of equilibrium, which is, say, extensive. Off-diagonal are exponentially small. And this was ansatz which was made by Mark Svidnicki, I believe in 96, that the full structure of many-body matrix element for any generic observable should look like this. So this is large expectation value coming with Kronecker delta, plus some function which depends on two variables. E is like mean energy, En plus Em over 2, and omega, which is energy difference, times e to the minus entropy over 2, so it's square root of density of states if you want, and maybe some fluctuating random variable with variance of the order of 4. So this is ansatz. It's not proven. So, and we expect that this f0, this function, should be slow function of overall energy. That's basically where we look in the energy spectrum of eigenstates, again, should not much depend on this energy. But it can be a quite strong function of energy separation. And we know that if we think about this as some operator which excites our system, then typically local operators can only excite a little bit. So it means that if energy between n and m becomes very big, they should rapidly decay. Okay. So now, if we look into fluctuations, we see that they at least become finite, because now I can write my sum over this O and m squared as an integral over final energy Em, but it's the same as integrating over omega, right? I'm saying that my Em will be En plus omega over 2. This is the definition of omega. So my initial energy En is fixed. I start from a given eigenstate. So I'm integrating over M. It's the same as integrating over omega. There's probably a factor 1/2 missing, but sorry for this. Then we need to take density of states at energy En, which is E plus omega over 2. Then this function squared, because it's square of the matrix element, and e to the minus s, and average of sigma squared becomes 1. So, and we see that at least this huge factor e power s indeed cancels, and what we get is actually d omega times integral of this f squared times e power beta omega over 2. It looks a little bit asymmetric, and actually I think I need to ask, there is a recent paper by Marcus Riegel and Finnick where they don't have this factor, and I think it's a mistake, or maybe they somehow try to absorb it here. But I think this factor is very physical. It just tells you that states with energy above n contribute more to your fluctuations, because there are more of them. So beta is the measure of density of states. So we see immediately that in order for the system to satisfy, in order for the eigenstate to be thermal, we need this function to decay at least faster than exponential. Because otherwise we can always find temperature where this will diverge. And this function does decay faster than exponentially. And again, it was checked for some models, but we can just see why it happens if we look into non-equal time correlation functions and look into and use our intuition. We know that non-equal time correlation functions basically exactly the same object as I was describing before, but now you have this extra factor En minus Em over it, because O is taken in the Heisenberg picture, right? So if I want to write this expectation value, e to the plus I h t, or e to the minus I h t o, at state n, connected, it's the same as sum over m not equal to n e to the I h t o, sorry, e to the minus I h t m o n. But because n and m are eigenstates of my Hamiltonian, I immediately pick up these factors. And then again I go to the integral. Instead of sum, I go to the integral. I have to keep in mind I have exponentially many levels, so the level resolution is never there. I use discrete levels only for convenience. I go to an integral, and then I recover same result as before, but with extra factor e to the minus I omega t. But then I can ask how this function should behave in order I reproduce typical behavior. And typically we have exponential behavior. So we exclude glasses and other non-ergodic systems. Well, we know that Fourier transform of exponent is Lorentzian. So we just see that in order to have exponential behavior at large times, it means that at small frequencies, we should get this Lorentzian form.
Could you go to the previous slide where the exponential factor came from?
Because we evaluate, you mean beta omega over 2? It's because my capital omega, which is density of states, is nothing by e power s.
I see, okay.
So, and if you expand s at small omega, you get beta.
You said that this was checked for some models. So
Yes.
What do you mean by that? I mean, it was actually computed?
Well, this was definitely computed for nuclei. And there, by Israeliev and Zelevinsky and others, people who worked in quantum chaos long before ETH, and they indeed confirmed that you get what's called Lorentz or Bright-Wigner function at small frequencies, and at long frequencies, we expect Gaussian tail. And this is basically comes again, from elementary quantum mechanics, we know that at short times, if you want, this is like a Zeno effect, all correlations should decay quadratically. So, and Fourier transform quadratically means it starts in a Gaussian way. And Fourier transform of a Gaussian is a Gaussian. So, it's faster than exponential, so it's okay. So, and since I will talk about fluctuation, dissipation relations and everything later, let me just say that in the same Srednicki paper in 96 or 99, he shows that using this ansatz for diagonal elements, which was before, you can recover fluctuation, dissipation relations and so on. So this ansatz is consistent with what we know in so many years.
So but that ansatz is just based on the fact that you're guessing that this
it was a guess.
Exponential.
But you should see that this guess was confirmed, as I said, by simulations in nuclei and other systems, small systems.
But is it obvious that, I mean, your correlation function is not obvious that it should be exponential?
Of course, of course.
It might not happen.
It means that if you go to glassy systems, our answer will be completely different. Okay, so how representative is time average? Well, again, so before I describe you the answer, let me just say, okay, let me just say what I want to measure. So I want to ask how long time average describes my observable at a fixed time. So following question. So what if I do many measurements with the same density matrix at time t? So I measure at time t, I measure again at time t, I measure again time t, and do many measurements. And I take average of the observable at time t. Then I do the same over a string of times, and now average the same quantity in time. And I want to ask how close these things are together. So if my thermalization hypothesis works, then it should be very small. Because we know that once the system thermalizes, it stays in thermal equilibrium. And indeed, it's a very simple computation once we understand what to do. So we basically want to compute average of observable at time t. It means observable with fluctuating exponent, with this oscillating exponent, and just diagonal part of the observable. So, and then we want to integrate this over time. So we want to see how representative my expectation value at time t, and we average basically mistake between given time and time average over time. So that's a typical way. So, and then you can just see that if you square this and average over time, so the only way to get non-oscillating terms is when either I choose this EM is equal to EN, but this will be cancelled by this term, or I will choose one of the M's is equal to, say, P from the other side. I have this sum squared, right? So I have 4 indices, MN and say PQ. And sum over PQ will have exactly the same terms, EP, EQ. So if we want, you have direct term and exchange term. So, and this exchange term will give me this following thing. It's rho NM times rho MN times rho MN times rho. If you want, just do this simple exercise, you will see that this is the only term which survives. And this is a good news, because I know that my matrix elements are of the order of e to the minus s over 2. And I know that also trace of density matrix squared is less than 1. So it basically means if I take this maximum value of OMN squared out of the brackets, which is still e to the minus s, the remaining sum converges, and I see that this is very small. So it actually means that my expectation value of the observable at long time t, average over all times, is exponentially close to true equilibrium. So it's not just I have thermalization in the sense that time average approaches equilibrium. I have thermalization that I'm at almost all times close to equilibrium.
I have a question. Actually, I got confused in the first equation. Even though you are taking a long time average, still the oscillating terms seem to survive.
No, but I integrate over time, right?
Yeah, so that is like taking a time average, right?
No, but I'm taking time average of different options. I compare the first thing. I take quantum average, if you want, or statistical average, over my observable at time t. So this is a fluctuating variable. Then I square it. And then I integrate over time. And I ask whether it's the same as if I first integrate over time and then square. And these two are actually identical up to exponentially small corrections.
Okay.
Yes?
If I'm an experimentalist, what sets the scale for my averaging? So,
Well, this is of course relaxation time. Eigenstate thermalization hypothesis does not explain things which were not explained. It just provides you new language.
no, I understand, but here you're averaging over it. So suppose that instead of taking the limit t going to infinity, you think define it, you want to know.
Oh, it's basically over. So you might imagine that if well, I'm averaging, if you want, I'm just removing oscillating terms. And you can imagine that basically if my average time is longer than relaxation time, I have basically zero contribution of off-diagonal elements to my observable. So why it happens is another story, but this is... Okay, good.
This quantity inside the integral,
Yes.
when you measure it, you just at different times you measure using different experiments. Right? Or
Yes, so if you do it numerically, you just know expectation value from one measurement. If you think about experiment, you have to perform many, many experiments to measure what's the average at time t.
no, I'm saying even if you want to measure at two different times because it's the integral over time,
Yes,
right? So,
always, yeah, but
so you want to at two different times, it's not the same experiment.
no,
it's a
at each time you do many experiments. You first fix time t, then you measure your observable many, many, many times. Then you found expectation value of this observable at time t. Then you do the same at different time.
different,
and a different time.
Starting from a different...
From the same density matrix. So we are talking about fluctuations of average. So you have, I don't know, some term like that, right? So now at each point in time, of course observable will fluctuate. This is just normal because we have density matrix, we have measurement noise, whatever.
Now my question is, suppose you want to measure there and you want to measure somewhere here.
Yeah, but I exactly compare the things.
But you'll, for these two measurements, you will start with different initial conditions?
Same density. Statistically they are the same,
Yes.
but of course they're different. That's why I mentioned density matrix. So density matrix tells us that each time I start from a new initial condition.
Yes, I understand, but I thought that if you make one measurement there, then you want to go to the t.
I do 10 power 6 measurement here, then 10 power 6 measurements here, then 10 power 6 measurements here,
So
starting from statistically same state.
So is it now 3 into 10 to the power 6 experiment you are doing, or 10 to the 6 experiment you are doing?
Well, it's 10 to the power 6 times number of time points when
Yes,
you're doing
that's
measurement.
the question.
So if I measure in 100 points, it will be 10 power 6 times 100.
That's your initial condition. That many initial conditions.
Yes, yes. I need that many. It's not something you typically measure in experiments, even though when you talk about quantum information or whatever, you are more interested in
No,
this.
the reason I am asking that if I do this in classical system, I will just do 10 to the power 6 initial conditions. Even if I have to measure at...
Well, in classically, it's the same story. You have statistical fluctuation, so
Yeah, but-
it means it's the same question. So I'm asking, so suppose I started my experiment and in 5 minutes I decided to figure out what's the average of my magnetization.
No, if I have to suppose measure at 5 minutes, 10 minutes and 15 minutes,
Yes.
I can start with the same 10 to the power 6 initial conditions, measure 10 to the
Yes.
5 minutes, again
Right.
go measure at 10 to
Yes.
10 minutes and measure at
Right.
15 minutes, right?
Yes.
In quantum system, am I doing the same thing? When I go to
Yes.
measure at 5 minutes, I just measure and then evolve the system from there?
No. It's different experiment. Classically, it indeed does matter. If I do a measurement,
That's
I can
yeah.
continue.
Yeah.
Here you have measurement noise. This I'm excluded. If you will have measurement noise, you will have much bigger fluctuations.
So if I have to measure at 3 points, it will be 3 into 10 to the power 6 initial conditions.
Yes. So each measurement is really new experiment. Okay, I still have some time. So now let me go a little bit closer to chaos. So how we can think about quantum chaos, or how people think about quantum chaos? Well, they just say, well, let's imagine that our Hamiltonian is actually random. And let's see what comes out from this hypothesis. So there is a huge literature on this, and I'm not going to cover it. I just want to say that one of the main results, at least main for me, is that you recover from this assumption that your Hamiltonian is just random matrix. You recover a very specific prediction that statistics of levels or level separation, it's normalized to mean, has a peculiar, it's called Wigner-Dyson form.
What is S?
S is level separation. It's normalized to 1. So it's distance between nearby levels. And then this is completely different from what you expect for non-interacting level. So random matrices and random energy levels are completely different stories. If you have random energy levels, you expect just Poisson statistics. It's like basically throwing a coin many times and just look into distributions between spacings, but because points are completely independent, you'll get Poisson statistics. Here you get something interesting. You get much faster tail. It's Gaussian, not exponential. But also you get repulsion at small levels. So this you can derive basically this or nearly this distribution for 2x2 systems. It's a simple exercise. But let me just show that we intuitively know why this happens, why there is level repulsion. So let's imagine that we have two energy levels which cross at particular point. So it means that in this basis, my density matrix will be degenerate. It will be E1, 0, 0, E1 something. Oh, sorry, not density matrix. My Hamiltonian will be degenerate. It's E1, E1, 0, 0. But now you imagine that any small noise in off-diagonal elements will immediately shift this degeneracy. So if I have independent energy levels, I have to require just these guys are close to each other. But if I have full matrix which is random, I also require that these two guys close to 0. They actually require more. And it's harder to satisfy both requirements. That's why I have level repulsion.
Can you give some intuitive idea why it is hard to satisfy both?
Well, because it's too much fine-tuning, right? So you have random numbers here. I'm just saying, if you have only random numbers along diagonal, then you just say, okay, these random numbers are close to each other. That's exactly what Poisson statistics. But here, you require that both these are close to each other, and also these are close to each other. So it's a stronger requirement. And actually, this Wigner-Dyson statistics was checked in many contexts. So this is what I mentioned, people studied heavy nuclei. So these are some heavy elements, I even don't remember which ones, and this is statistics of 1,726 level spacing. And this is actual data from a long time ago. This is a Poisson statistics for reference, and this is Wigner-Dyson. And you see that it works quite well.
So, just to be sure, so this is just the probability distribution of the spectrum of a random Hamiltonian drawn from this.
Well, this is random Hamiltonian,
yeah.
And this is actual data.
Yeah.
So, and you just see they agree very well.
You have a fully chaotic random entrostal matrix. Is the fully chaotic has it also figured in the Wigner-Dyson, or Wigner-Dyson is just the fact itself?
No, you just see that levels behave as if the matrix is fully chaotic. You know it's not fully chaotic, because nuclei are described by well-known forces. Well, it's still complicated. Well, there is a much simpler system. It's a Sinai billiard, so you know it's a very simple object. You have a square well and a hole in between. 2 by 2. So it turns out to be classically chaotic system. And you can just ask, what's the statistics of high energy levels? And amazingly, you recover the same result. So even though it's just single particle Schrodinger equation, once you analyze it levels, you'll see Wigner-Dyson statistics.
Is there some kind of universality in this?
Yeah. This is pretty universal.
No, I mean, like in regards of critical phenomena, something like that?
Let me go a little bit further. I'll show you 3 more examples, and then we will guess if there is universality. Okay, this is another example from 80s. Hydrogen in a strong magnetic field. Well, we know hydrogen is a simple atom, which we study in undergraduate quantum mechanics. But if you put it in a strong magnetic field, it becomes very complicated. And if magnetic field is very strong, I guess by now you are not surprised that it's Wigner-Dyson statistics. This is experiment. Okay, so now about universality. This is histogram of spacings between bus times arrivals in Mexico. So if this is universality, it should cover this problem as well.
Some outliers.
So this is data, and this is Wigner-Dyson. Interesting paper. If you know, please don't answer the question. If you don't know, please, I just ask you, does anyone has a guess why there is level repulsion, time repulsion? I mean, if you go to Germany, it won't happen like this, right? Or Switzerland, you'll have a delta function. So you have to go to some other country. But in Mexico, I'm sure, like here as well, and maybe in Italy, I don't know. You can check. Well, at least in certain parts. These are private buses. Maybe this will help. So what's the reason for repulsion?
They wait for passengers.
Huh?
They want more passengers. So if they see that there's a bus going, they just wait.
Yeah, exactly. Because if there is a bus right in front of you, you just want to wait a little bit to get some passengers because you don't want to go empty. So it's precisely the reason. And amazingly, this reasoning just leads to this universal prediction.
So public buses are the top.
I don't know data for public buses, but I assume that public buses, especially in Switzerland, will be precise delta function. Well, in Italy, it will be probably Gaussian, right? Well, in Russia, for sure, it will be Gaussian. It's very broad distribution. Good, but for this one, I even don't have any intuition. This is spacings of billion zeros of the Riemann zeta function. Riemann zeta function is an interesting object. It's connected to prime numbers, but why it has such a perfect Wigner-Dyson distribution of zeros? I have no clue.
What's the x-axis there?
Hmm?
What is the x-axis?
Which is?
What is the x-axis of the entry?
This is this one?
Yeah.
It says 0. Oh,
The x-axis.
that's a good question. Well, I mean, apparently this is normalized spacing. Apparently this data is taken at very, very large numbers. No, this is normalized spacing between zeros, normalized on the mean. You go to very, very high numbers where I guess this mean was well defined. I don't know details about this one.
So these are zeros along imaginary.
Yeah, but they only have zeros along imaginary. That's the fact about Riemann zeta function. So let me just maybe wrap up slowly. That I showed you this nice picture. Maybe to answering your question, is there universality? Unlikely, because I'm now going to many-body quantum systems, and whether if they would be related to buses in Mexico, I would be very much surprised. Who knows? Maybe things are much simpler. And I talked actually about classical systems in many examples. Some of them. So, well, let's take many-body quantum system, and this is like a particular one-dimensional system of hardcore bosons with next nearest neighbor interactions and hopping. This model was used a lot by various people, in particular this I'm taken from Marcus Riga and Leo Santos' work. And the nice thing that you can tune integrability by changing T prime and V prime. And this is like a snapshot, whatever, a bunch of snapshots of what happens with statistics of many body energy levels as a function of T prime, which is basically a parameter which breaks your integrability, which, if you want, makes you more and more ergodic. And you see, originally, the system is completely integrable. It's not ergodic, and I'll talk more about integral systems later. But as you crank up this number, you just see that level statistics becomes more and more Wigner-Dyson. And what they checked, that if you correlate where statistics becomes Wigner-Dyson and where you see thermalization in terms of observables, the correlations are nearly perfect. You cannot say for sure because these are crossovers, there's no thermodynamic limit, system size are small, but at least from the data it looks that these things, so onset of ergodicity is the same as onset of randomization. There is even a nicer, I would say more surprising example. It's also from the work of Lea Santos. So if you take same, it's almost the same. Hardcore bosons, they're like interacting spins. I don't want to go into details. So they take basically integrable spin chain and add just one impurity. So they have, if you want, 18 spins and take one local impurity. And it turns out that if you put this impurity in the edge, it's like changing boundary condition. It doesn't change integrability. So the system's still integrable. But if you put it in the middle, you break integrability. And it turns out that you just see when it's on the edge, you have perfect Poisson statistics of levels. When you put it in the middle, you have Wigner-Dyson. It's amazing that one impurity completely changes statistics of levels. So this example is without impurities. No. This parameter breaks integrability, but this is, we want global parameter. So it's like second nearest neighbor hopping. So here it's just local in space. So just to illustrate. Okay. I think I'll finish with this slide, maybe just to set the stage for tomorrow. So I just told you that you can understand quantum ergodicity as a property of eigenstates. Then I told you that this may be a property of the spectrum of the Hamiltonian. But classically, we know that ergodicity implies delocalization. So tomorrow, I will try to convince you that, in the beginning of tomorrow's lecture, I'll try to convince you that in a way we can think about quantum ergodicity as also delocalization. And there is a very, very simple example, my, I guess, favorite example of non-integrable system. It's precisely a system which Tisha mentioned as non-interacting Ising-spins. It's actually even simpler because they're non-interacting. So these are basically arrows which point either up and down. And I know my dynamics is very simple. Each spin is conserved. Very simple integrable dynamics. But we ask a question. So what if we take some typical state with fixed magnetization? Well, actually we know from standard statistical mechanics that this state will look perfectly so. That's actually how we derive, if you want, normal distribution and Gibbs distribution for spins. The integrability is not important at all. But now, okay, let me skip this. Now let me imagine the following. So let me do a local quench. The local quench means I take some spins in the middle, take them, and just flip them. So you just see what I did. I took the spins in the box and changed red to blue. And if I didn't mess up, it should be exactly like a mirror image. Well, and we know that this is atypical. It's not so. And with my simple dynamics that each spin is conserved, it will never thermalize. So actually, thermalization should mean that this state should sort of delocalize among eigenstates of the Hamiltonian. And so, as I will start tomorrow, we can think about ergodicity as a delocalization in the Hilbert space. In this sense, quantum ergodicity is not that different from others. Okay, I guess I stop here. Is there any more questions?
Could you go back to to the slide where you derived the formula for delta O squared in terms of this integral over f squared?
Yes.
Is it previous?
Yes. Yeah.
So,
Maybe.
yeah.
Yeah. Okay.
So in this, the delta O squared is not suppressed thermodynamically, right?
So which is suppressed?
Delta O squared.
Oh, it is. What do you mean suppressed?
I mean,
It is suppressed because of this factor, e to the minus s over 2, but it's enhanced because they have many states.
Right. So overall, in the final expression, it's not suppressed by an entropy factor.
Yeah, and it should not, because we know that fluctuations should be extensive. They shouldn't be exponentially small, exponentially large. So basically, this fact just more or less fixes entropy dependence. What remains open is how this function behaves. So this function, as I argued, is basically Fourier transform of canonical time correlation functions. So if you have very slow correlation functions like power law, this function will have singularities and maybe very similar to what Alessandra said, like Fermi H singularities and so on. So when I was saying this function is Lorentzian or Gaussian, I was talking about typical situations when you decay exponential.
But somehow the intuition that we have for large system is that if I measure the pressure or some other thermodynamic variable in a system, it should be sort of very fine-tuned to its average, right? So in some sense, even this fluctuation at any given time should be small.
Right, but it will be small as 1 over, no, this fluctuation, if this is extensive variable, then these fluctuations will be extensive. It's actually already seen here, because all fluctuations are connected correlation functions. And connected correlation functions are always extensive, if you want. You can just see it because even in simple classical systems, when you have connected correlation functions, you subtract basically mean squared. And well, think about a high temperature expansion Ising model, right? So you have e to the minus whatever beta h, and you do high temperature expansion. Connected correlation functions are only those which have the same point. If you do Feynman diagrams, you also have always connected correlation functions. So connected basically means extensive. So it means that the whole thing for extensive observable will be proportional to the volume. But then if you take square root, it will be square root of volume as normal. But these things are okay.
Okay.
So besides chaotic versus integrable, are you aware of any other properties of the dynamics of the system that we can tell just by looking at the statistics of the eigenvalues?
Whether it's a unique indicator, I just don't understand the question. So experimentally, you cannot look into statistics of eigenvalues. You just really look into observables.
Right. But even theoretically, if you're saying that I can look at the statistics of the eigenvalues and say, oh, this is chaotic.
Yeah. Well, there were no counterexamples as far as I know, because in principle, you can imagine that what if my eigenvalues have Wigner-Dyson statistics, but they're so close to each other, they're exponentially close to each other, then none of the reasonable timescales is sensitive to them, right? Because when I said that we are average over time, of course I cheated. Because if my energy levels, I have 100 particles, my level separation is 1 over 2 power 100. So in order to completely average, I have to wait for time much longer than the time of the universe. So of course this was cheating. So, but then I can say, okay, maybe it's not important because there are off-diagonal elements of nearby states. They're always zero. I cannot excite these states because they're so similar. Otherwise, they would repel each other. So maybe it's not important. So, and maybe I'm exciting only high energy states.
So can you check that in the Fermi-Pasta-Ulam problem at small beta, the level spacing does not satisfy the Wigner-Dyson distribution?
You mean quantum Fermi-Ulam?
Yeah.
Just a second, so let me finish it. So, and then you can imagine that maybe, even though this nearby levels of Wigner-Dyson, when I go to relevant time scales, I will see something which is completely regular. It doesn't happen numerically, and I don't know why. So answering your question, don't know, by energy levels you mean, how do you define that? You talk about quantum Fermi Pascal?
Yeah, let's take that interaction and write it on a finite lattice with some level spacing. So that will have some big Hamiltonian which you can look at the level spacing of. And then
I don't think it has been done, because the problem is that Fermi Pascal is a tricky problem. You have many continuous degrees of freedom. So it's not the problem which you can easily discretize. So what you can do, you can write both. I mean, even for one particle, you have already infinite Hilbert space. Well, you may be cut it off, but it's, and then you have many particles. So normally we like to work with discrete models. It just turns out that there is a model which becomes very similar to Fermi Pascal. It's both Hubbard model, because both, if you want just coupled Josephson junctions. So coupled Josephson junctions, you have interaction energy which is m squared and tunneling which is cosine of gradient phi. And if you are in a regime when vortices are not important, so gradients are small, you do your expansion up to gradient phi to the fourth, and you exactly get this problem. But again, so the problem is that you need to go to very high filling factors, and at high filling factors you can use DMRG, you can use some methods, but they don't give you access to energy levels. So it's very tricky. But my guess that you're right. They won't be Wigner-Dyson.
Also, could you go to the next slide? Sorry, the one with the time average.
This one?
Right, yeah. So here you're not comparing the mean squared, the delta O squared at different times, just the average of O at different times.
No, I average O squared over T. So again, what I'm doing, I start my experiment, and this is actually it's some sort of cartoon, because quantum system doesn't even have one curve, right? If you measure, we project system, but anyway, so it's some cartoon of experiment. Then I go here, and I measure my average. Then in a separate set of experiments, I go here and again measure my average. And measure average again. And then I compare this average. I'm asking how this average will fluctuate.
Yeah.
And this average will not fluctuate, basically.
So you're not sort of taking into account the fluctuations of the operator at each of those.
Yeah, but those are there already.
Yeah.
So those are sort of those will be standard statistical fluctuations. Because you see, if I know that my time average is the same as typical time, and I also know that time average is the same as statistical ensemble, that's what I was basically trying to show you, then I know that my observable here behaves exactly as statistical ensemble. So by doing this sort of small steps, I find what I want.
This direction was the one that you had on your previous slide, the expression that you had on your previous slide, the delta O squared.
Yeah. So this is the normal average if you want.
Yeah.
And now I just said that this normal average, whatever, which was there, so this normal average is representative of one state.
So the stability ansatz is crucial towards arriving at the result of vanishing fluctuations, is it?
Not vanishing, not diverging. If you don't make this ansatz, you will get here exponentially big number, because you see, you have exponentially many terms. There is no way you can get finite answer without this analysis.
How does that relate? I mean, does the integrability or lack of integrability of the Hamiltonian play any role?
Of course, and this, I will talk about this tomorrow. Right. It's very important.
That does play a role. Normally
It plays huge role.
So when you compare this level statistics, it is Wigner-Dyson. So here only you look at the level spacing. What about the Wigner semicircle or the full distribution, joint distribution?
Semicircle is a little bit hard, because you have to choose some window, because your density of states, overall density of states changes. I'm not aware, if Alessandro knows, if anyone did. In principle, it's doable. The problem is that you have finite number of states and they're spread over many energies.
When you do these calculations, you always have the trouble that you have to. So essentially, the density of states of your many-body system is not a constant,
Right.
as in the matter matrix. But it's not even a semicircle. It's some complicated thing. So in order to get these curves, what you have to do is first a trick that is called unfolding. So you essentially have to rescale all your level spacing, renormalizing the density of states in order to make it. And
Yes.
then once you do this, then you compute the level statistics.
Right.
And you get this kind of curves. But if
But
you don't
also-
do unfolding and you just compute straightforwardly your spectrum and the level statistics, you will never get this nice.
But also, I think you have to be careful because it's known, for example, from Anderson localization and this type of problems. You have Wigner-Dyson statistics only within levels which are within the Staulis shelf.
Yeah.
Outside, you have Poisson statistics.
Oh,
so
that's true.
and
It's also not
you have to be really careful. So I think if you want to check this, what you have to do, you have to choose window where density of state doesn't change, and you have to be window which is smaller than inverse relaxation time. So that basically this sets the scale. And within this window, I think you will recover semicircle
well,
laws.
it's always tricky because you have small systems.
Right,
So
but
you have to
number of levels is 2,000 or 3,000. If you reduce the window, you reduce already to 200. And actually, it might be even less, so it's 100. And then,
So
I don't know.
sometimes what you do is
Tricky.
you choose the central third of your spectrum. So you have a few thousand levels. You choose the central third. So you have 1,000. And then you do this unfolding procedure to rescale out the variations in density of states, and then you get these curves.
So unfolding means you just subtract some average?
You have to take into account that the density of states is changing with energy, so you cannot just straightforwardly average.
And that's what also they do for Riemann-Zeta zeros?
No, that is a different story. Riemann-Zeta zeros.
I mean, so they are going
I'm
to
telling you what
I actually don't know what it is, semicircle one for you.
for many body Hamiltonians.
But it must be the case, right? If you see such a perfect statistic, it's hard to imagine it comes from something else.
Because, the thing is, in random metrics, you have this semicircle distribution, which is practically, close to the center, it's close to flat. So then if you go to the tails, then all this nice level spacing, etc., are complicated. You have tracy middle tails and all sorts of complications. So you want to go to something.
You understand there cannot be semicircle, right? Because if you don't do various things, because you have a bunch of levels here, a bunch of levels here, a bunch of levels here. So at the end,
if you just subtract a mean
maybe, yeah, but you have to take into levels which really repel each other, but not because you have bunches of levels which don't talk to each other.
Okay, let's head